Well, hello friends. So, in the last class, we have learned the basic Dalton model, Thomson model, Rutherford model, scattering experiment, and we have understood quite a bit of the atom. But as you know, there were drawbacks of Rutherford, which was explained in the previous class, and well, Bohr came up with another model, very interesting, and that's it. We are going to learn from that. So here, well, the dates are also important. In 1913, Niels Bohr, Danish physicist, introduced the revolutionary concept of quantum concept to explain the stability of atom. So if you recollect from the previous class, the Rutherford model did say that there is space between the nucleus, which is having protons, and positively charged nucleus, and with some proximity you have the electron. And as we have seen that the electron in the proximity of the finite proximity of the nucleus will readily get attracted and fall down to the nucleus if it is stationary, and if the electron by some means is in motion within the proximity, then we have seen that it is going to spiral down and come to the nucleus. Let's suppose all of you recollect the diagram there. That is the nucleus, which is got a positive charge, and if there is an electron here, negatively charged electron, and if it is in motion, then it is going to spiral and fall down into the nucleus. And we have discussed this aspect, and this is what they say the system is unstable. Okay, so what it means here is that if at all the electron is here and the nucleus is here, and this proximity, that is the electron is here and the nucleus is here, this proximity has to be maintained, and that is what the Rutherford experiment has shown. That is, there is vacuum between the nucleus and the electron. But now, going by the classical mechanics, classical electromagnetic theory, this electron cannot stay if it is stationary, and if it is in motion, this electron will spiral down because it is going to continuously radiate energy. And therefore, at this point of Rutherford, model fails because it is not able to explain how it can become stable. So now you see there is a proximity, that is, there is space between the electron and the nucleus. There is no doubt about it. The Rutherford experiment has clearly established that. But now the question is, if the electron has to be stationary, I mean, if there has to be if the electron has to be at some distance from the nucleus, then the only way is that it should move in a circular. The electron must move in a circular. But if it is moving in circular path, then it has an acceleration, centripetal acceleration. It is accelerating, so it will radiate energy and collapse like this. So that is where the the Rutherford model failed, and scientists were struggling hard to explain. Incidentally, Planck came out with the quantum theory. So that means now energy is now quantized. Energy is quantized. Okay, we'll learn more about it later. But Niels Bohr made a very bold statement. You can see the expression here. The old classical laws which are applicable to the bigger bodies cannot be directly applied to subatomic particles such as electrons and protons. See, the word here is bold because you see the electromagnetic theory is in existence for almost a century or more, and suddenly Niels Bohr, an young scientist, comes and says, look, the classical laws with which many interesting phenomena could be explained. Now he says, well, you can use that for larger bodies, but when it comes to subatomic particles, you cannot use the classical laws. So he said, well, as long as the electron is in a particular orbit, that is, if the electron is revolving in a pre-designated orbit, okay, not anywhere, but in the pre-designated orbit, then this electron will not emit radiation. It was a very bold statement because a new theory was being created here. Okay, and that's how it is. Now you can see the interesting aspect about it, because that means now, according to him, as long as the electron, see now, this is nucleus, if the electron is revolving within this designated orbit, not arbitrary orbit, designated orbit, this orbit, or say this orbit, or say this orbit. These are all designated orbits. There is a way of calculating the radius of these orbits. We'll soon come into that. So as long as they are confined to these orbits, okay, they will not radiate energy. That is a very bold statement made by Einstein. And well, very interesting developments. I just read out. In physics, a quantum, plural of quanta, is the minimum amount of any physical entity, that is physical property, involved in an interaction. The fundamental notion that a physical property can be quantized is referred to as hypothesis in quantization. Okay. Albert Einstein won the Nobel Prize for proving that energy is quantized. Just as you can only buy shoes in multiples of half a size, so energy is quantized, that is multiples of the basic fundamental quanta. Quantum theory is the theoretical basis of modern physics that explains the nature and behavior of matter and energy in the atomic and subatomic level. Precisely what I explained. And the nature and behavior of matter and energy at that level is sometimes referred to as quantum physics or quantum mechanics. So we have learned Newtonian mechanics so far in the first year classes or the 11th standard or PUC 1. And now what we are learning, what we are going to use here is a new theory called as quantum theory. So please appreciate and understand that this theory is applicable to the subatomic particles such as protons, neutrons, etc. If the bodies are bigger, then we will apply the Newtonian mechanics. And of course, there are still issues where you can't apply both. There is one more theory called as Einstein theory, etc. Okay, right now we'll confine our discussion to quantum theory. So there is a new theory called quantum theory, and we are going to use that theory and explain the stability of the atom. Quantum level may refer to energy level. A particle that is bound can only take on certain discrete values of energy called discrete energy level. As I pointed out here, these lines that I have drawn here, I am calling it as orbits, but frankly speaking, they are also, that means the electron that is here has certain energy, the total energy. The electron that is in this orbit has certain energy, the total energy. The electron in this has different total energies. They are all quantized energy levels. So, energy level, a particle that is bound. See, this is important. The particle is bound. That means there is binding energy between the in the system. The electron is bound to the system, just like how moon is bound to Earth. Okay, it cannot move away from Earth because it is bound to Earth. The same way, the electron is bound to Earth. A particle is bound can only take certain discrete values of energy called the energy levels. Of course, I said moon, but we are not applying the quantum mechanics to moon, but similar to that. That's what I said. Don't mistake me. Quantum realm is also called quantum scale, a physics term referring to scales where quantum mechanical effects can become important. Right. The main properties of quantum mechanics are the quantification of energy. That is, we are going to say this is the minimum energy level, just like how you see the minimum currency. Right now the minimum currency in India is 1 rupee. So whatever currency we say are multiples of 1 rupee. The main properties of mechanics are the quantification of energy, the wave-particle duality, that will also be explained by this quantum theory. That is, a particle, we can say electron in some context as particles, and in some context we'll have to say electron is a wave or a wave function, to be more specific, because some phenomena can be explained by considering electron as a wave, and some phenomena can only be explained if you consider electron as a particle. And this quantum theory is quite handy, quite useful in explaining the wave-particle duality of matter. And of course, there is a wonderful theory called uncertainty principle. We will be that is also based on this quantum theory, and the correspondence principle. There is one more principle, well, just that I have mentioned. Connection to big idea about energy, electronic transition atom correspond to quantized energy. So we are going to make use of quantum theory in all these things, and we find different properties of quantum mechanics that is used in these different phenomena that we can explain. The quantum physics governs the way the universe behaves at a scale of atoms, as simple as that. Okay, so quantum physics governs the way the universe behaves at the scale of atoms, electrons and protons. Quantum physicists put the rules of quantum world to test and devise ways to stretch their boundaries. Okay, so here you see the quantum physics governs the way the universe behaves at the scale of atoms. That is, if you now consider an atom itself is like a universe. See now, right now we have got sun. All the planets are revolving around the sun in their pre-designated orbits, and we call this as a solar system. Similarly, atom is a system, right? But it is at that scale. The scale is, atomic scale, very, very small. So in that scale, if we have to discuss how this system is existing, the stability of the system, then the quantum physics governs it. Right now, for our explanation of the solar system or the universe, we are making use of Newtonian mechanics and of course the other things like Einstein special theory of relativity, etc. So Niels Bohr and Max Planck, two of the founding fathers of quantum theory, each received a Nobel Prize in physics for their work on quanta. Einstein is considered the third founder of quantum theory because he described light as quanta in his theory of photoelectric effect, which we are going to learn eventually in the year 1921. Okay, this is in brief about the quantum theory, and I have used this word quantum many times because I want to drive in your head that it is a different theory other than different from the Newtonian mechanics. Okay, and the basic difference is that an electron which is revolving around the nucleus in its pre-designated orbit, even though it is accelerated because there is centripetal acceleration, it is not going to emit radiations. Its energy is fixed. And classical electromagnetic theory will say that if any particle, any charged particle, if it is accelerating, it has to radiate energy and lose energy. This is not happening here. That is basically the quantum theory. Okay. Now, the postulates of Bohr theory is very, very famous and very much pertaining here. As you can see here, the electron now is considered to be revolving in circular orbit. Minded students, now we are learning the Bohr theory, so we have to consider the electron is moving in perfect circle. As we learn more about it, okay, we cannot stick to the condition that electron is always moving in a circular path. That is, as far as we are learning Bohr theory, we have to say it is moving in circular path. Now further, you see, this theory got refined, and ultimately what we are learning in the next few sections is Schrodinger's wave function. So according to that function, electron exists around the nucleus. That's all. Electron exists. Now, whether it is moving in a circle or that and this, well, only the Schrodinger wave equation can tell something about it. Okay, so there is nothing sanctum about the circular motion of the electron. But as long as the question is based on the Bohr atomic model, then we have to confine our discussion and say, well, it is going to move in a circular path. I hope I have made it very clear. And of course, all of us know the basics mechanics. So if now you have the nucleus where we have got the charge in ZE plus, and we are only going to consider hydrogen atom. So of course in hydrogen atom Z is equal to 1. Z is equal to 1 in hydrogen atom. And we are going to, Niels Bohr has given a model for hydrogen-like atom. What do you mean hydrogen-like atom? That means now if you take hydrogen, there is only one electron and one proton. If you take helium, there are 2 protons and 2 electrons. Now what we do is we knock off one electron or we ionize the helium ion. So then what happens in the helium ion? Z will be equal to 2 in the helium ion. But since we have knocked off one electron, there will be only one electron, and we call it as hydrogen-like atom. So helium ion will now be called as hydrogen-like atom. Similarly, lithium, if you knock off 2 electrons, then it will also be called as hydrogen-like atom. So now, if you now consider something like this, so okay, I will start with the hydrogen atom itself. So it has got only one proton, okay, and there is electron which is revolving around it. So it is charged. There is charge on the electron E, and there is charge here. And if we take, I will take hydrogen-like atom. So I will still use ZE here. Then obviously we know from the electrostatics. Of course, you have not yet studied electrostatics. So just like how two particles or even bodies, okay, which are separated by finite distance, say r, not equal to 0 and not equal to infinity, finite distance, and so if they possess mass, then they start getting attracted towards each other. This is what is called as the gravitational force. So by the virtue of mass, there is force of attraction between the masses. Okay, and we call this as gravitation. And all of us know that the gravitational force, I am just giving you the magnitude. We write it as G m1 m2 by r square, where m1 m2 are the point masses, r is finite distance between the two particles. We know this, we have already studied. Now here you see we have two charges. So here the electrostatic force, I am representing it as E. Of course, I am not teaching the Coulomb's law in detail. I am just mentioning the Coulomb's law here in its scalar form. So here G was the constant of proportionality. So you have some constant of proportionality K, which depends on the medium. Only thing is G is independent of the medium, whereas K is dependent on the medium of separation between the two charged particles. And in this case, the charged particle is the electron, negative charge, and the proton, it is ZE plus. ZE plus is the charge on the proton, this is charge on the electron, and divided by r square. So here this distance becomes of course the charge on the electron is negative, we get this as negative. So as I told you, I am only considering the magnitude, I am writing this. So what is this? This is the force. And in this case now, from Rutherford experiment, the mass of the proton is approximately 1000 times the mass of the electron. So for all practical purpose, you know this, and that too when it is ZE, this will be very, very heavy compared to that of a lone electron. And so therefore, due to this force, the electron will experience an acceleration. So acceleration of the electron will simply be Fe by the mass of the electron. So as you can see here, the acceleration is right here, and Bohr has assumed that this electron is already in motion. So that means now this force is nothing but the centripetal force. So this force, that is this one, will be the net force acting on the electron, and that will be equal to the centripetal force on the electron, and v square by r. Okay, so that means now he has used the Newtonian mechanics, and he has established the centripetal force necessary to keep the electron in its circular orbit is given by the electrostatic force between the electron and the protons. That is his first postulate. Okay. Yeah. Now, second thing is, as all of you know, this electron has also got mass, okay, and it has got velocity, and it has got proximity r. And therefore, with respect to this point, the center of the atom, we can now say that, well, this electron has got angular momentum of the electron mvr, and this angular momentum is conserved. Let's recollect that Earth moving around the Sun, we have studied that. So now Earth is moving in an elliptical orbit around Sun, with Sun at one of its foci, and the most important thing is that the angular momentum of Earth is conserved. That is why, you know, and why the angular momentum is conserved, because the force between the Sun and Earth, the gravitational force, is always acting on always radial. That means if you take, this is the elliptical orbit of Earth, and this is Sun. Whether the Earth is here or here, the force is always along the radial direction. And as you know, this is called as the central forces. So as long as the central forces are acting, then the angular momentum is conserved. So in this case, it is circular motion. So in this case, the centripetal force is also the central force, and therefore the angular momentum is conserved. This is the postulate of Bohr. So he said mvr is equal to nh by 2, and this is also written as m. This is the symbol that is used, h by 2 pi, we use it. Well, Bohr did not substantiate why this postulate. Okay, we have explained this because there is a necessity for centripetal force, and that is given by electrostatic force. Fine, that is accepted. But he has not given explanation why he has used this equation, second postulate. But nonetheless, he has used it and he has proved. Okay, he has proved the existence of atom and the stability of atom. Okay, these are the two postulates. So as you can see here, the first postulate, centripetal force required to encircle is given by the electrostatic force of attraction, and the constant of proportionality that I used here, K, is 1 by 4 pi epsilon, where epsilon is the permittivity of free space. Now, permittivity of free space and all you will learn in the next chapter, that is electrostatics in detail. Right now, you just have to understand that, well, if you take, you see in physics, you know, we call a cat because it has the properties of a cat. Okay, So we look at the properties. So the medium around that is, if you take the medium around me, so it has got several properties. Okay, you can say the mass of the air, the density of the air, so many things, viscosity, all those are properties. And there is also some properties which I am going to teach you in the next chapter, called as permittivity, permeability. These are all different properties. So here it is pertaining. So the permittivity of free space, epsilon naught, that is one of the properties of the space between the two charged bodies or two charged particles. One of the properties of the space between the one charged particle and another charged particle. And in this case, free space means it is vacuum. So the permittivity of free space is denoted by epsilon naught, and its value is so and so. All these are given, okay, and that's how they get related. Okay, the second postulate, as I have just now mentioned, is that the electrons can revolve only in those orbits in which the angular momentum of the electron about the nucleus is an integral part. Okay, mvr is equal to nh by 2 pi. Okay, the second postulate. And let's come to the third postulate. Electrons in an atom can revolve only in discrete orbits called stationary energy levels or shells. So you can see here that around this nucleus the circles are drawn, and we have written here E1, E2, E3, En. So that means now these are the orbits, and these are also representing the, in this case it is showing the path in which the electron is moving, and here I would like to mention it is also representing the energies of the electrons, total energy. So electrons in an atom can revolve only in discrete circular orbits called stationary energy levels. Why stationary? Because the energy of this is fixed. Energy of the electron, as long as it is moving in this orbit, is fixed, and it is not radiating. That is why he is using the word stationary energy levels. An electron in a shell is characterized by definite energy, angular momentum, and orbit number. N is equal to 1, N is equal to 2 are the orbit numbers, and here you see the angular momentum of the electron in the first orbit will be 1, that will be simply h by 2 pi. In the second orbit it is going to be 2h by 2 pi. The third orbit it is going to be 3h by 2 pi. So that is precisely what is mentioned. While in any of these orbits the electrons do not radiate energy, although it is accelerated. Very nice postulate. And now comes the fourth one. Now, electrons in the outer orbits have greater energy than those of the inner orbits. This is something which is quite evident, but nonetheless, just like how you see, if I take this object, say if this is Earth and this is the object, if I take it, as I keep taking it away and away from Earth, supposing my hand is Earth, then its potential energy goes on increasing. Alright? So similarly, the potential energy of the electron, as it keeps moving away and away from the nucleus, keeps on increasing. Of course, the speed also will change, but as it is known here, the electron in this energy level is more than the total energy in the lower levels. Okay, so that's it. The orbiting electron emits energy. Orbiting electron emits energy from outer orbit when it only jumps from outer orbit to inward. Supposing the electron will jump from higher orbit to lower orbit. If at all the electron jumps from higher orbit to lower orbit, then it will, during its transition, it is going to emit energy. Okay, now it is very clear here. You see, an orbiting electron emits energy when it jumps from outer orbit to inner orbit, higher energy state to lower energy state. Okay, and that means now you see this now the nucleus is here. This is the higher energy level. This is the lower energy level. So if an electron is in this orbit, say En, and this orbit, the energy here is En minus 1. If the electron jumps from En to this orbit, then it is going to emit energy in the form of a photon. Okay. Now here you see this energy level, En energy level minus the next energy level. What is the next energy level? En minus 1. So that means now the electron is going to jump from higher energy level to lower energy level, and this difference energy level, this one will now come out of this atomic system in the form of photon, in the form of photon energy of frequency nu, that is h nu. So nu stands for the frequency of the electromagnetic radiation that comes out of the system. That is what he has said. Okay. At the same time, what he says is, if you want to move the electron from lower energy level to higher energy level, if you want to move it from lower energy level to higher energy level, then you have to give energy to this electron. Electron will absorb the energy and then move from lower energy level to higher energy level. Okay, so that is precisely what he said in this, in his postulate here, and also absorbs. So this is this equation I just now wrote it. The energy absorbed or released is always in the form of electromagnetic radiations. This is what he said. The energy absorbed or released is always in the form of electromagnetic radiation. This is one more thing that Bohr said, and later on you see it's not true, because the electron can receive energy from other forms, that is thermal energy, and it can be a fast moving electron. If it bombards, then also the electron can jump from lower energy level to higher energy level. So this is about the Bohr model. I hope all of you understood. If you have any questions, please ask. Okay, no questions? Fine. Thank you. So I'll call it as the end of the day today, and we'll meet tomorrow. Thank you very much.